Hey everyone, I'm just gonna do some standard Stoic or somewhat standard Stoic problems, and I hope you all get a feel for this. So the first question I'm gonna do is a multi-step reaction one, where in both steps the theoretical yield is not 100%. So there's multiple ways to approach this problem, but the way I find most intuitive is you calculate the theoretical amount, and then you apply all of the actual yields. So to give you some more context, if we read the question here, it says, in the first step, phosphorus and oxygen react to form diphosphorus pentoxide, and that's this reaction. And then in the second step, diphosphorus pentoxide and water react to form phosphoric acid. This one and this equation. So it now gives us the actual numbers we will be calculating with. Suppose the yield of the first step is 62%, and the yield of the second step is 70%. Calculate the mass of phosphorus required to make 1 kilogram of phosphoric acid. So since we have these actual yields, we know that, of course, there's going to be a significant difference between the actual amount and the theoretical amount. And when we calculate it, we need to ensure that the amount needed is taking into consideration these percentages. So to start off, I'm going to start by calculating the theoretical mass of phosphorus. So this could be set up very simply by using your dimensional analysis. So 1.0 kilograms of phosphoric acid, H3PO4, is 1,000 grams. And then this can be just converted into moles by dividing by the molar mass. And I'm actually going to do this on the calculator, just so I can store these values for later. So 1,000 divided by H3PO4, so 3 hydrogen plus 1 phosphorus plus 4 oxygen. I'm gonna go back and correct my hydrogen. All right, so now we know that we approximately have 10.2 moles of H3PO4. You will want to more than 3 sig figs. However, since I'm using a calculator, I can use the store function to get this entire decimal. Okay, now we only know the moles of phosphoric acid, but now we need to figure out the amount of diphosphorus pentoxide, which is this amount. So using your dimensional analysis skills, you can figure out that there's 2 moles of phosphoric acid for every diphosphorus pentoxide. So now I'm simply going to divide this value by 2. And now we shall move on to this equation. So a way to think about these 2 reactions going on simultaneously is just imagine a container, and it has all of these. It has all the phosphorus 4s, oxygen 2s, P2O5, 3H2O, oh, not just H2O, my bad, and H3PO4. So this Alex problem is remaining in the range of, like, there's no like backwards reactions, so you only have to worry about the just all the reactants being using up. So basically, oxygen will react with phosphorus to form the diphosphorus pentoxide. Sorry, I keep on writing it incorrectly. And then all of these will immediately just go and react with the H2O to do H3PO4. So all of the diphosphorus pentoxide produced by this reaction are immediately going to go to this one. So therefore, even though like there's a 1 coefficient here and a 2 coefficient here, we won't need to account for that. We will only need to account for this 2 coefficient within the actual equation itself when we're solving for that phosphorus. Okay, so now I'm actually going to solve for that phosphorus. And since there's a 2 in front of the diphosphorus pentoxide and simply 1 in front of the phosphorus, all we need to do is divide by 2. And that will leave us with 2.55 moles of phosphorus theoretically needed to make 1.0 kilograms of phosphoric acid. So yeah, we have the theoretical value, but now we actually have to find the actual one. And that is where it gets slightly tricky. So I'm briefly going to diverge from this question a bit. So in probability, there is a theory or theorem called the sum of multiple probabilities, or I'm probably saying the rule wrong. But it basically is like, if you want, for example, you have a coin and you want to find out what the likelihood is that you'll hit like heads 2 times in a row, you would do 1/2 times 1/2 equals 1/4. But here we're doing something with percentages. However, this concept is still the same. You have a 62% yield and a 70% yield. And in order to find the total yield, instead of like adding, which would give you a value greater than 1, and doesn't make sense because you can't just like suddenly create mass, you're actually going to multiply. You're turning these percentages into decimals just so it's easier to work with, and you multiply. And now you should have a value of, give me a moment, 0.434. Or in total, this is your percent yield, which is really bad, as I might preface. But yes, because you have to take into account that this 62% is for this first reaction. And that means that you're only getting 62% of the total phosphorus. And then this compounds when you have this second yield of 70%. And so now you must multiply them together to account for both. Okay. So you have the total percent yield, and you have the total theoretical amount of phosphorus needed to get 1 kilogram of phosphoric acid. So now what are you going to do? Well, what you're going to do actually is you take the amount of phosphorus you theoretically need it, and you're going to divide it by your your percent yield. Yeah, sorry. And this in turn will give you the amount of phosphorus you actually need. So it may seem a bit intuitive. Wait, why are we dividing and stuff like that? But here, let me show you what's actually going on. So what's going on is that the 2.55 moles of phosphorus 4 can be set up in a ratio such that if 2.55 mole P4 is equal to, sorry, I forgot the percentage. Let's pretend it's like 4 something, 0.44% yield, then what about then what about the amount of moles that we would need for a full yield, which would be a yield of 1? Because remember, these are percentages. So this would be 100%, and this would be 44%. And so if you do cross multiply everything out, you'll get to the same place as before, this ratio. And that is why it's just division, because you're just going to end up back where you started, 2.55 divided by 0.44. So now that we have this final value, we just need to turn this into the actual mass of it instead of just the amount, which is moles. So we just do a simple multiplication with the molar mass of phosphorus. And now we have 728. So to account for the sig figs, I'm just going to do 7.3 times 10 to the power of 2, and then add the unit symbol of grams. All right. Next up is a precipitation reaction involving a substitution, single substitution. So, okay, it's basically asking us the original concentration of copper 2 sulfite, given that 141 milligrams of the copper precipitate were found, and 350 milliliters of copper 2 sulfate were used, with the other quantities being unknown. So this reaction involves a backwards approach. Basically, we have to use the mass that we're given of copper, turn it into moles, and then use that to find the molar amount of copper sulfate. And then if we read the question, it wants the original concentration, not just molar amount. And this concentration is unique because it's asking for grams per liter rather than the molarity that we're used to. So therefore, we'll have to take the moles divided by the amount of liters, and then multiply by the molar mass to ensure that we have grams over liters. So let's do it. I'm just going to go through it very quickly since I believe we're all clear on how to approach this problem. So right now I'm just going to be finding the moles of copper by dividing. And then since all of the coefficients in this reaction are 1, we don't need to account for any molar ratios or anything like that. So I'm directly going to divide by 0.350 liters because you have to do that unit conversion. And I will get my molarity of 6 millimole about. But since we do have to multiply by the molar mass of copper sulfate, it's going to be different. You set it up in such a way. And here is your concentration, or more so the original concentration of copper sulfate before it was all reacted. Double check. All right. Sorry for the small cut, but here we are again. So this is question number 3 and the last question that I'm going to show you guys today. This question is asking, suppose 1.28 grams of sodium bromide is dissolved in 100 milliliters of a 47 millimolarity aqueous solution of silver nitrate. Calculate the final molarity of bromide anion in the solution. You can assume the volume of the solution doesn't change when the sodium bromide is dissolved in it. Be sure your answer has the correct number of significant digits. So I think the first thing everyone should know when they see this equation is that both of the reactants at play, silver nitrate and sodium bromide, are ionic compounds. So when it asks the final molarity of an anion in the solution, what ultimately we're looking for is there a net ionic change? And so you all can check this with your reference packets, but I'm going to do this with a brief Google search. Hold tight for just a moment. I'm pulling up my solubility chart. All right, silver bromide. All right, so although sodium nitrate doesn't seem to precipitate in water, or sorry, be insoluble in water, silver bromide does appear to stay insoluble. So we now have a conundrum on our hands. How do we figure out the final molarity of a bromide anion in a solution when we know some of it is going to react with silver, the silver anion, to form a solid? So we can set up our net ionic equation this way. We have NaBr, and this is going to be Na plus Br minus. And then we have silver nitrate, and it's going to be represented by Ag plus and NO3 minus. And as we've already determined, silver and bromide are going to be insoluble in water. So that means that, that instead of being a pair of ions, it would just be a solid. And so this means that bromine is no longer an ion in the solution and should be subtracted from the total amount of ions. And the other one, Na and sodium nitrate, is going to be soluble. So this one will stay as ions. So now we can see that our total net ionic change is simply this. And now what? Well, if we know that there's 1.28 grams of sodium bromide in 100 milliliters of 47 millimolarity solution of silver nitrate, we can now determine the concentration before the reaction of each ion. And that can be done by looking at the chemical formulas. We see that per formula unit of sodium bromide, there's one sodium cation and one bromide anion. That goes the same for silver nitrate. So assuming this, we can then say that the molar amount, the amount of moles of sodium bromide is exactly equal to the concentrations of sodium and bromide. Same goes for silver nitrate. So let's go do that. So if we take a look, we can do 1.28 divided by the molar mass of sodium and bromine. And we have about 0.012 moles. All right. Well, what about silver nitrate? And we can go calculate this by doing something slightly different. So first, let's address the two unit conversions that will need to be done. 100 milliliters is equal to 0.1 liters, while 47.0 millimolarity is simply equal to 0.047 molarity. Now that we know these, we can set it up in such a way that the units will cancel out to give us moles. Because if molarity is moles over liter, we can then multiply molarity by liters to give us moles. And I'll do that right now. So now we know that we have 0.0047 moles of the Ag plus ion. So now that we have these two amounts, what now? How much will be actually created of silver bromide? So what we have to consider now is that the amount of silver bromide created is dependent on how much there is of both substances. This goes back to the limiting reactant and the excess reagent. So if we take a look at our two values here, I apologize, this is slightly small. We see that there's significantly less silver ion present than the bromide ion. So therefore, we can expect that silver will be the limiting reactant in this case. And that means that the amount of silver bromide form is exactly equal to the concentration of the silver ion. Therefore, the amount of bromide consumed, the bromine anion consumed by this reaction will be exactly equal to the concentration of silver. Therefore, we can then subtract the amount of bromine anion by the silver cation to find the amount of excess bromine anion remaining, which will then give us the final molarity after we divide by the 100 milliliters of solution. So if we just do this, and now we should divide by liters instead of milliliters, so I'll just do it for conversion. And the reason I'm doing this is because the question is specifically states that that the volume will stay the same when the sodium bromide is dissolved. So therefore, just do this. You can find our final molarity of bromide, and it asks for significant digits. And if we consider this, we notice that our 100 milliliters is converted into 0.1 liters. However, there should be 2 zeros after this to account for the three significant digits of milliliters. However, I'm not sure how Alex is going to approach this, so we shall find out. So I am going to estimate that they may want 3 sig figs on this question, or maybe not. Okay. Let's see. Your answer has the wrong number of significant digits. How could this be? All right. Well, I believe we've all learned a useful lesson today, and that's be careful with your sig figs, guys, because even though you may be right, the computer may be wrong sometimes. Anyways, see you. All right. Keep up the good work.